I'd like to conclude our discussion of electric field and the introduction of the potential by calculating the energy stored in a system, which we use the capital letter for the purpose of this course, W sub E, to represent. This E refers to the fact that it's of the electrostatic stored energy. As you can imagine, later on when we talk about magnetostatics, there's also the magnetic field stored energy. So this is the total amount of energy stored in a volume of charges. So if we have a system with a bunch of charges, the total amount of energy stored is the amount of energy it would take to assemble all those charges if you move them in from infinitely far away. For a bunch of point charges, the total amount of energy stored would be 1/2 the summation of each of the point charges, Qm, times Vm. Here, V represents the potential associated with that point charge. So if you have Q1 over here, V1 is the amount of energy it takes to move Q1 from infinitely far to this location, and then you have Q2 here, then V2 is the amount of potential stored when you move Q2 from your reference point up to here. So you add all those up, that gives you the total energy in the system. If we were to rephrase this in terms of charge density, that is another common kind of calculation that we have to make to find the stored energy. In that case, if we're talking about, say, volume charge density, it would be rho V times V dV. So we can also rewrite this in the form of a volume integral. Now recall, we also have a way of expressing the charge density in terms of the electric field, or the electric flux density. Namely, the divergence of the electric flux density gives you the volume charge density. So if you substitute this in and then apply some vector calculus identities that I don't want you to be too concerned about, it's also in the textbook in section 482. But point is, if you substitute all of this in, you can end up at the quite elegant result that the energy stored is also going to be equal to the volume integral of the electric flux density dot the electric field. Or since the electric flux density is going to be equal to epsilon E, the total amount of energy stored in a volume you can calculate as 1/2 epsilon E squared dV. So this is a nice little result where if you want to find the total energy stored in a system, one of the first examples that we'll see in the next few chapters is the case of a capacitor, is if you have the electric field everywhere, you can simply take this square at every location across the entire volume, multiply it by epsilon, integrate it over the course of that whole volume, so add up all these little electric field values you have for the entire volume, divide it by 2, and then you have the electric energy stored in the electric field, due to the electric field. I'll also just write this out too. It's also 1/2 the volume integral of d dot E dV. The other thing is we use uppercase to describe this. Another concept is the energy density. So if you wanted to find this in just a very small piece of volume, then that would simply just be removing this integral. So the energy density in a given location would simply be 1/2 d dot E, or 1/2 epsilon E squared. So these are some key equations to keep in mind. Now, taking all this into account with everything we talked about before gives you kind of a workflow for a general chapter question. So general set of workflows that you would have for a generic question that goes over this chapter. So you would start with a system. So you'd be given a system of charges. So these can be in the form of, they might give you the charges themselves in point charge form. I might give you the electric flux density, or I might give you the gradient, the divergence of electric flux density. So I might give it to you in the form of charge density of volume, or surface or line for that matter. But the point is you're given a system of charges, which means that there's a certain amount of energy stored into it. So you would use all of the skills that you had previously in the electric field chapter to find the electric field. And then after that, you might be asked to find two things. Once you have the electric field, you might be asked to find the potential. So then you would take the integral of E dot dl to find the potential, or separately, you might be asked to find the energy stored in this system of charges, in which case you would do the volume integral as described here. Another type of question is maybe I'm given the potential. So I'm told what all the elevations are for the region of interest, if we're using the mountain elevation and gravity analogy. And I want you to find all the downhill arrows, right? So so you might be given the potential and then told to find E. And E would simply just be what? That's right. So it'd be negative the gradient of V. So you just take the gradient of the field of the potential that you're given in order to find the electric field. And then once you have the electric field, similar to the previous question, you might be asked to find the energy density. So this would be the general workflow that uses all of the concepts that we've learned in both the potential chapter and the electric field chapter.